Now, okay, let me just recap what we have done so far. So in the first session, what we did was that we broke down the language. We broke down a language into its components, and the components is what we called as the tokens. And we saw that the tokens can be of different types. Uh, I can consider a character as a token. I can consider a word as a token, and then I see that in the modern days we are considering part of a word as a token. So things like earlier we used to consider run and running as two different tokens, but now in the modern LLMs we are considering run as a token and ing as a token, and then I can fix these two tokens together to understand that this is a single entity. So that was the first session in which we did tokenization. Then we saw different kinds of tokenization, which has got benefit in not only English and other languages, how they are hampered if I consider word-wise, because they may not have delimiters like space, etc., like Chinese, Japanese, Thai, and all these languages. So how do we do tokenization there? Anyway, we got down to the units. We had a technique by which we could break the words into tokens. And then what we did was that once we had the tokens, then we started seeing whether we could find meaning in those tokens. So initially we found that there is absolutely no relationship between any tokens, the way the machine understands it. Like it considers them as one-hot vectors, and one-hot vectors are basically perpendicular to each other. And so there is absolutely no meaning in them. So it is just about considering them as separate entities. That's about it. It doesn't understand any semantics. Then also when we did a count-based approach like TF-IDF or count vectorization, then also it was having no semantic understanding. It is just the frequency based on which it says, okay, fine, you are more frequent, so you must be a popular word. You are less frequent, so you must be a rare word, and things like that. So, and these have very limited applications. Like they have applications like, for example, spam detection or sentiment analysis, etc. But this it is not really understanding anything about language. Then gradually we moved, in the last session, we moved to a stage where we saw that we were able to give a semantic meaning to the words, and we understood the CBOW, continuous bag of words algorithm, in which what I was doing was that, I'm giving some surrounding words to the machine and telling them these are the surrounding words, and for these surrounding words, this is the word which it is surrounding. So I'm giving him, sorry. Okay. Yeah. So let's say, for example, we took the example that, let's say I went for a walk, walk. So I give him a sentence like this, and I say that, okay, fine, this word for, it has got two neighbors on the left hand side. One neighbor is I and one neighbor is went. And one on the right, I have got a neighbor called A and a neighbor called walk. So now I told him that supposing I make a data set like this, I say that if I have the words I, want, and walk, if this is your data, and for this data, the word it is surrounding is for. So it forms like this. Similarly, I can say that I, for, and A are the surrounding words. In this case, the word which I'm looking for is went. So now you see that by this technique, what I've done is that I've basically converted this abstract problem into a supervised learning problem where I have data and I have the labels. So if I create such a data of a huge proportion, then from this data, the machine can understand that he has to make a mapping from such kind of a data on the left hand side to a label on the right hand side. So by doing this, it understands what are the kind of words which surrounds a particular word. From understanding the words which surround a particular word, it can make out that this is the possible meaning of this particular word. It doesn't understand what for actually is, or what orange is. Orange is a fruit or a banana or a animal. It doesn't understand that, but it understands that orange comes in between these kind of words. So it is finding geometric meaning in whatever data I'm providing him. Okay, now what we do, that was the CBOW approach. It's a very big breakthrough actually in natural language processing, this CBOW. But then what happens in CBOW is that you understand from the, if you remember from the lecture, when we were creating the neural network, what I was doing was that I was creating a neural network. On the left hand side, I was putting the different words. So these are becoming my inputs. Like for example, this is I, this is want, and this is for, and this is walk. So these are my inputs to the neural network. And to these inputs, what I do is that I multiply them with a weight vector. So I multiply them with a weight vector. So this is W. And this vector will have a size of the embedding size. So it will have a size of, let's say, 3 by 3 by V, or N by V. Now, come on, Aditi, that doesn't work. Yeah. And I cannot go in the window mode because it is painful to operate Zoom in the window mode.
Oh, acha, okay.
Okay.
ठीक है, but I'll keep on searching and I'll share
No,
with
it is a bug by Microsoft. So you'll have to
No,
write.
but we'll have to find a way. And
Yeah,
I'll be on the
yeah,
top of it.
yeah,
Yeah.
we have to find a way. Anyway, so I have to find this particular representation of the word, and somehow I have to do that. So what you remember is what we were doing was that we had this weight vector, and we multiplied the input vector with the weight vector to obtain another matrix like this, another column vector like this. And then what I did was, a very important thing you must remember is that I averaged it out, right? I did an average at this stage. Now, when I did an average, what happened was that the individual words, their context is lost because I am averaging it out to a single unit. Okay. Come on. Okay. So this particular step was the painful step in CBOW, where by doing averaging of these inputs and the multiplication with the weight vector, I'm actually losing the individual words context. So if you remember slightly, try to, or go back to the video once again and watch the demonstration or the notebooks I've shared with you. You can watch the notebooks. The thing is that when I make a prediction, it is actually not able to consider the order of the words, or it doesn't understand which word came before or which word came afterwards. All it knows is that for is surrounded by these 4 words. In what order these words are happening, it has forgotten, because it has averaged it out. Okay. Now this was the problem. So now we will try to eliminate this problem. And another problem which CBOW has got is that now you see that this step is the problem, basically because when I'm doing the averaging, I am losing context in terms of which is more frequent, which is less frequent. Right. And in fact, when I average, the words which are more frequent, they will dominate over the words which are less frequent. So in CBOW, what happens is that if a word is rare, then it is totally lost by the machine. It replaces it conveniently with something which is more popular. A popular example we give is that, supposing I have a word like delightful. Now you understand from normal English is that delightful is a word which I use less as compared to the word beautiful, right? Though they are different in meaning, but as far as contextually it goes, they can be utilized somehow contextually in the same way. So now if I want delightful as a word to be understood by the machine will conveniently forget that, and whenever I want something which is delightful, it will tell me beautiful. So this is a popular example which we utilize. Okay, so we will try to overcome this problem, and to overcome this problem, today we will discuss a very important architecture called the Skip-Gram architecture. So I will take you step by step through the Skip-Gram architecture, and we will see how the machine understands the language based on the Skip-Gram architecture. Now, guys, today we have a lot of people from my new batch. I started a new batch today in IIM Kozhikode. So we have a lot of new people. These are enthusiastic people. I'm very grateful they've joined us. But then you may find it little difficult because the topics which we are discussing is little advanced, but it can help you in terms of understanding the overall picture of how a machine operates or in terms of artificial intelligence arena, and you can still benefit. I believe that. I will try to keep it as simple as possible and keep it I will try to balance between technicality and non-technicality. Okay, and you can ask questions anytime you feel like. So this is what we're going to do: skip-gram architecture. So now in skip-gram architecture, what we do is that we flip the problem. We flip the problem. Like this was CBOW. I'm giving a particular word and I'm giving him the context words. So from the context words, it has to understand. It has to tell me what is the word which is the target word, right? So this was CBOW. Now I flip the problem in skip-gram where I give a target word. I give a target word and tell the machine, tell me what are the context words for this target word. Like I give him the target in a sentence like I like orange juice and drink and eat eggs every day. I give him the word orange and tell him, okay, fine, you tell me what are the words that are surrounding the word orange. Okay, it is just the opposite of what we were doing in CBOW. In CBOW, I was giving him the context words, like I'm telling him eggs, eat, etc., etc. And you tell me what is the target word which I'm looking at. Like I'm telling in this particular sentence, I hide this particular word and I give him this word, this word, this word, and tell him, okay, fine, tell me which word I have hidden from you. That is CBOW. Now I'm flipping the problem. I'm telling him that I'm giving you this word, and this word. You tell. Sorry, I'm very sorry. What I'm doing is I'm giving you this particular word, and you tell me what are the words which are surrounding it. So he has to predict and tell me that this word, and this word is surrounding the word which I've given it. So now let us see how the machine does that. Am I clear so far? Any questions? Yes, Eknath.
Sir, I understood. Like, okay, skip-gram is complete opposite of CBOW. Just wondering, like, okay, use case perspective, where will be using skip-gram and where will be using CBOW? Like, any example sort of thing you wanted to share?
Yes. The thing is that actually skip-gram and CBOW, they belong to a larger family of algorithms which we know as the word-to-vec algorithm. Word-to-vec. Okay. Okay. Now, Eknath, your question is slightly not correct simply because you see the context in which we are operating right now is that, okay, first let me finish this. So word-to-vec operates in two different modes. One is CBOW and one is skip-gram. Okay. Now, Eknath, don't take it otherwise. What do you call? Slightly, I should have explained the context a little bit better. Then this question would not have come. Simply because what we are trying to do is that at this point of time, I have taken my corpus, I have broken them down into units. Let me call the units as words, and then I'm trying to make a representation for each word in such a manner that the words which are close in meaning to each other, they appear close to each other, right? And they appear in the same context for the machine. That is all I'm trying to do. So what I'm trying to do is that I'm trying to create an embedding, and the embedding is basically a vector, and these vectors for the words, if a word like boy, girl, king, queen, etc., these vectors it should be close to each other, saying that we are similar words. That is all I'm trying to do, because I'm not trying at this point of time. I don't have the ability just with the vector representation of the words to create an application. Now, what we will do, I knew such a question would come up. So what we will, it is too early today, but what I will do in the next class is that next class I will discuss another mechanism of word representation, which is the technique called global vectors. And then we will use these embeddings that we create. Right now we are creating embeddings. So we will use these embeddings that we create to create a model which will write text for us. Okay. Now, do you have an idea regarding how to utilize these things in a use case? Eknath?
I think, sir, I'm getting it. Looks like okay. I'll try to summarize my understanding. Not sure, like okay, right or wrong. Happy to be corrected. So, fundamental thing what we are saying is like okay, we have a word to vector. We, as part of embedding, we have converted into more like a vector, and now based on the nature of the problem. Example, like okay, we have to find a word in between a sentence, so we can follow an approach of CBOW. And if we got a word or context and we wanted to find the surrounding words, so we can potentially use skip-gram. So these are two set of problem, but the fundamental approach of solving the problem is slightly different, maybe different formulas, but the base remains same.
Okay, I can say that your understanding is correct, but there is one important correction which I need to make. Now, thing is that I have shown you in the last session also that ultimately I will take all these words and I will try to make a neural network. Right, I will try to make a neural network, and in this neural network, basically, I will have a hidden layer and then I will have an output layer. So I will have something like this, and then after I optimize my neural network to get this proper hidden layer, which is my W. Now, this is what is the embeddings of the words which I will extract from this neural network. Right. This much you remember? Anyone has
Yes, sir.
a doubt regarding this? No doubts, right?
No.
All clear, sir.
Okay. Now, my intention was to find this embeddings of the words. That is, how should I represent the words? After I get this, I will actually discard all this. Okay. I will discard everything of this. Then I take these embeddings and then I will start making applications. Let's say one application I'm making is that I am not able to show you the application because Hugging Face has changed its storage policy, and as a result, my data I cannot upload to Hugging Face right now. I have to do it in AWS or something like that. Now the thing is that I have to make the change. Now, thing is that I made an application where Novartis gave me a lot of data regarding their clinical tests. Okay, so when they have a new drug discovery, they conduct clinical tests, and from the clinical test, they will determine whether the drug can go live in the market or not. Now, the clinical tests, they are very expensive because they have a lot of planning to be done. Then they have to find candidates who will participate in the clinical test, who will be agreeable to take the dosage of that medicine even before it is commercial and before it has got regulatory approval and everything. So it's a very expensive process. Now, what happens in the real world is that um, to plan the clinical test itself takes about 7-8 months or maybe 1 year also. So a lot of money goes into that. So now what my problem was that, which was given by Novartis, was that you use machine learning. I will give you the data regarding all the previous clinical tests which we have performed, and I will give you the details of the new clinical tests that I'm trying to perform. What you do is that you read through all the historical clinical tests and tell me top 10 historical clinical tests which are very similar to the current clinical test. Okay. If I get the historical data regarding the earlier clinical tests which are very similar, then what I will do is, instead of studying a huge amount of historical data, I will focus my study on this top 10 historical clinical test. I will understand how we went about this, what was the challenges, what was the winning strategy, and all this kind of stuff. And then I will plan my new clinical test. Now, if I do this, what this particular job, which is if done humanly, would take around about 7-8 months. When I do this using a machine, it takes hardly 1 hour or 1.5 hours. Okay. Now, the problem is that I have to read the text in the historical clinical test and determine whether they are similar to my new clinical test or not. Now, how do I do that? Machine does not understand language. So, what is my best bet? What I do is that I find the embeddings of the words which is used in the text of the clinical test. And I teach the machine how to find the embeddings by using techniques like CBOW or Skip-Gram. So I get this. Once I get this, I understand the machine has some semantic knowledge regarding the language which I have utilized. And then from that understanding of the language, I present him a clinical test and my new clinical test. Then I say that you read the words in the old clinical test and the new clinical test and tell me whether there is a match between the two or not. Now do you get me, Eknath?
Yes, sir. Now it is. This is actually I was looking for. Thanks for clarifying. I think now I can connect the dot.
Anyone else has a question at this stage? Do you understand what we are trying to do? One thing should be clear to you, that machine does not understand your language. I have to make a mechanism by which he can understand my language. And even after this stage, you will realize that for the machine, our words have got no meaning. Predict, whether it's a verb or a noun, he doesn't know, but he knows predict has to do something with the context. Yes, Devashish.
Sir, is semantic, I'm sorry, is the embedding and vectors are same? Both are same or they're different?
No, the embeddings are basically vectors.
But vectors are not embeddings.
No, vectors are vectors. I will show you the demonstration. It will become clear. I think I can clear this doubt. Give me a little bit of time.
Sure, sir. Thanks.
Yes, Sandeep.
Sir, what if those clinical trial example you gave has numbers, let's say 30% of the patient showed this against 20%?
No, a language means both text and numbers, everything put together. So
Okay.
he will understand the word 30 also. He will understand the numbers 30 also.
Okay, got it.
You can try this. In ChatGPT, you say, please tell me what is 5 plus 7. It will answer you 12 because it understands numbers.
Okay.
Okay. Now let us get down to the implementation. I think things will become more clear rather than being abstract like we are having right now. Okay. So what I will do is that I will first show you how we build the network. How we build the network, and then I will build the complete network. Okay. So what I have is that I must have some kind of a vocabulary. So I am taking a very simple vocabulary of a very simple corpus of one sentence. Normally, you understand corpus basically means the text or based on which I will train my machine. So corpus is normally a very, very huge data set. Like I take the complete works of Shakespeare, or I take the complete tweets over the last 1,000 days. These are corpus. So, but for demonstration purpose, first what I'm using is I'm using only one sentence as my corpus. So this is my sentence. I like orange juice and eat eggs daily. So from this corpus, what I do is that I extract the vocabulary. So the vocabulary basically I'm doing a word word level tokenization. Just wait a minute. Let it start off. It is to assign yeah, it has done it. So word level tokenization means I get my token. So this is one token, this is one token, and so and so. So these are my tokens. So if I have a very large thing also, I will do the same thing where I will take out all the different tokens. So right now, I see that I have 8 different tokens. So my vocabulary size is 8. I want to make embeddings of the size 3. That is, I want to make vectors. I want to make vectors for each word of size 3. That is, I will have 3 elements inside my vector, right? So each word has to be represented by let's say it is 2, 3, and 1. This becomes one vector. Do you appreciate that, all of you?
Yes.
Yes. So I like you saw in the initial example, I represented boy as 222 and king as 288. So this is my representation. We did this, right? So I am trying to create vectors for every word. So this was boy and this was king. Okay, and if you remember from this particular thing, I made the machine understand that since this, at least on this parameter, both of them are the same, that means both of them are males. That much I could make the machine understand. Okay, but this was artificially done. Now what I'm trying to do is that I'm trying to do it more naturally, and I'm trying to create vectors of size 3 to represent each word. So that is my choice. So I'm telling him my vector size should be 3. Okay, so once I've done that, what I do is that I have to get the context. Like I told you, this is my sentence. I like orange juice and eat eggs. So what I will do is that I will take each word and find the neighboring words of these words. And this has to happen on a window. So I have defined my window size as equal to 2. So that means to say that for this word I, the context words are like and orange. So for this word like, the context words are I, orange, and juice. And for the word orange, it is I like and juice and so on. So I'm creating this context words. And so now you see that for every word, I have a training pair. Like I has got like, I has got orange, like I like orange, and so on. So this is clear so far. How we did this? Any doubts? Okay, I assume no doubts. Okay, I have created my training data. Now I like we did in CBOW also, I assign arbitrary weights. Totally at random, I am assigning weights. Now these weights are assigned at random. This is the matrix which I basically want. This W matrix is what I exactly want. You see that I have 8 words, and this matrix has got exactly 8 vectors in that, and each vector will ultimately represent each of the word. So this vector, the first vector should represent I, the second vector should represent like, and so and so. But since I do not know what this should be, I have given absolutely random numbers. I will make the machine understand by some mechanism what they should be, and the machine will make its formula for giving the right choice of vectors for every word. That is our goal. Okay, once I've done that, I now take a particular word as a target word, juice, and for this word, I pull out the context word. So for the target word juice, the context words are like, orange, and eat. These are the 4 surrounding words. So if you do not remember, just look at this. So juice is the word. So on this side I have like, orange, and on this side I have and eat. So I have taken this. Now what I do is that I one-hot encode. Now this again from the last class, you remember, I one-hot encode so that I can isolate, right? I can isolate the vectors. So one-hot encoding is basically having a 1 in one place of the particular word and remaining all being 0. So I do the one-hot encoding of juice. So this is what I get. Now what I do is that I will show you the neural network, then it will become more clear. I project this target word into the vector space to make my hidden layer. So my hidden layer becomes this particular vector. Okay, this is the same size as the embedding size of the word that I'm looking for. Okay, after having created the hidden layer, I can compute a score. The score will basically tell how good or how bad my estimation is at this point of time. Okay, I generate a score, and you see that for every word I have a score. What are these scores? These scores are how similar the word juice is to all the other words. Okay, then again you have to recall things. Now you have this, we are building up, so you must recall the previous sessions. So then what I do is that these scores are not very informative. So what I do is that I change these scores into probabilities. So if I have probabilities, then everything will add up to 1. And if it adds up to 1, then I will have knowledge of which is more, which is less. Right? That is why I do the softmax. The softmax basically gives you probabilities. Now you see that since I did this absolutely arbitrarily, all the probabilities are almost equal, but still there is something like this probability is higher as compared to this probability, and so on. So what does it say? That if I take my particular instance right now, it says that for the word juice at this point of time looks like I, and eat are likely to be the context words, likely to be the words which are surrounding. That is what the machine thinks. So am I clear so far? Do you have any questions? Okay. So based on that, let me just show you. So this, you see that it is telling me that these are most probably the words which are surrounding the word juice. Okay. So if I now compare what is the real situation and what is the machine thinking, so actually the words which are surrounding are these ones, but the machine thinks these ones. It has not learned much about the language at this point of time. Okay. So since it has not learned, so let me just check how much it has learned and how much it has not learned. So it is still making one mistake at this point of time, but nevertheless, that's still okay. Okay. So on a overall scale, right now, the learning of the machine is about 0.5. Okay. The learning of the machine is about 0.5. That is, it is not very highly trained at this point of time. Okay. Now we will close this step by seeing what the neural network looks like. So neural networks looks like this. So I gave him one word juice and it created a hidden vector. This is the embedding I'm trying to create for the word juice. And from this embedding, it is, oh, what happened? Yeah. From this embedding, it is basically telling me that these are the probabilities of the words which are going to surround it. It is putting them in the descending order, right? Now, my objective is that I should create this particular layer in such a manner that this order of the words which I get is exactly the way I gave him in the training data. Do you get it? Anyone has any question? Anyone would like to paraphrase me so that I understand that you are understanding? No? Okay. That's too much of a ask, right?
Yes, actually, Partha, I think I understand, but paraphrasing would be too much.
Okay. No issue.
Yeah. Well, so what we are trying to do is basically get that embedding vector fine tuned in such a way that we can do auto encoding. So get back the original data. So original data here is the actual order of the word switching the window to window slice that we had, right? So that word is what it needs to predict in the order.
Yes. Yes, correct. So you guys understand the intent, how we are trying to teach the machine the language. So you should see what I'm trying to do is that if for a given word, the machine is able to understand what are the words which are surrounding it, then it has got a good chance of understanding what this particular word means. Do you think that's a decent way to teach the machine a language? Without telling him what actually juice is. He doesn't know juice is a liquid or a gas or a solid, or it's a fruit or a monkey or a animal, and it understands nothing. But it knows that the word juice is always hanging around with these particular words. Yes, Aditi.
Partha, it would also depend on the kind of corpus we are feeding, right? So if like the kind of data that we are training it on. So if we are, let's say, talking about in medical terms, this juice might mean something chemistry related or something biology related. But if we are talking in, let's say, cooking related things, then it might mean something else. So it is also dependent on the corpus, is it not?
Very important point. Very important point, and very important point to note also. It is that the machine will only understand the context of the words in respect to the data I feed him. Right? This is exactly what you are talking, Aditi. So if I'm training the machine on cooking books, he will understand the words in terms of cooking books only. If I'm teaching the machine in terms of manufacturing manuals, then he will understand the words in the manufacturing manuals only. That is the reason I was telling today morning in a class also that supposing I'm making a system, I'm making a machine understand language in a oil and gas industry where they have log books, and I want to read the log books and understand what the people are writing in it, and I want to predict whether there will be a disaster happening very soon. Then I must train the machine specifically on the language of the word book, of the log books. I cannot use a general purpose a general purpose tool like ChatGPT or Gemini or Claude to understand how the oil and gas industry works. I have to make a specialized system for that. Does this give you insight into what to expect and what to build in terms of industry applications? Yes, Aditi.
Yes, Partha. And similarly, I'm just thinking that what kind of a corpus ChatGPT or similar large language models must have been built upon. So, are they feeding each and everything around the world to them?
No, ChatGPT, when it started, the first version of ChatGPT, when it came out, it basically took the Wikipedia. It took something on a data called book 1, book 2, book 3, book 4. Now, what is book 1, book 2, book 3, book 4? These are unpublished books. Okay. These are corpuses of unpublished books. So these were the main two data sources for ChatGPT. Then it, of course, in the later versions, it took other public data sources also, like newspapers and things like that. So now, there was a huge complaint about ChatGPT in the initial days that ChatGPT is very leftist. In fact, even right now, also ChatGPT, many people say that it is very leftist, like because the nature of the data what was fed to ChatGPT to understand the language was basically coming from more leftist kind of writings. That is why it has learned to be a little bit leftist. Yes, Eknath.
So I was just going through this image and just a question on that. So this is a great association. What we have is like softmax probability score has been aligned across juice association with a multiple different words. So the highest probability is alike and lowest probability is the juice, which is that's how I could read. But one observation I noticed is like the word eat and orange. I think their probability is same. That's how I could see, like, okay, a dot 125001. I think orange is also same thing if I'm able to read correctly. So my question was like when we have like, okay, this softmax outcome, we can have an association, the highest probability and lowest probability we can probably understood. But if any word which is having similar probability score, how they've been potentially dealt around, just a question.
Now, having absolutely similar probability is very, very, very difficult. What you are seeing as the same probability is because I have rounded it off to 6 digits of decimal. Okay, but actually in real world, and also this corpus is very small, only about 8 words. Vocabulary is 8, whereas your vocabulary will be in millions, right? So having similar probabilities is absolutely impossible actually. But even in this case also, these are not actually exact probabilities because this is rounded off at 6 places of decimals. So if I take the complete number, it will be different. Even if they are the same, that means to say that I have to find within my window what are the most likely context words of the word juice. I'm looking for 4 words. So if I have 2 words of the same probabilities, I will take them together. I will say that these 3 are the highest probability and these 2 are the 4 are the fourth highest probability. So these 5 form your context words. Is that a reasonable estimate?
Yeah, fair enough. Thank you, sir.
Okay. Now we have seen that how I am setting up my neural network. I have only shown you how I am setting up my neural network. But right now I have not trained my machine to learn the language. The next step what I'll do is that I will teach the machine how to learn the language. Now I have come to the stage where I will teach the machine how to learn this particular language in this particular formula which I have generated. So again, I will go a little quicker. So I take my vocabulary. This should be clear to you by now. I have these words, same words, same sentence. So I have a vocabulary of size 8. Now I'm trying to make embeddings of size 3. Now what I do is that I get the context words. I get all my training sets. So this is also should be clear to you now. Third is I create my one-hot encoding function. I give initial weights. So I have given these. So these will be the final outcome which I'm looking forward to. and then I create my softmax function. I'm just defining it right now. Now what I do is that in a neural, you saw the neural network, right? So in the neural network, the people understand I have to take a forward pass, make a calculation, I will make mistakes, and then I will take a backward pass. In the backward pass, I will try to rectify my mistake. Again, go in the forward pass, make a prediction. Again, I will check whether the prediction is correct or not. If it is not correct, I will take a backward pass and try to rectify, and I will continue this process till I am 100% confident that I've got the right answer. So that's why I'm defining my forward pass. After my forward pass, I define my backward pass. Now, this particular back and forth, I am trying to train the machine to do. So now I trained my machine. So the machine went through 500 epochs of training, that is 500 rounds of training on the data. After training, let us see what is the learning which it has got. So if I plot the loss function, you see that initially it was making a lot of mistakes. Loss function basically tells me what is the kind of mistakes the machine is doing. So you notice this graph, it was initially making a lot of mistakes, and gradually it started learning, and then it is almost making no mistakes. It is making mistakes, but very little. Okay, that part is all not very that technical, but now let us see. After learning, what did I ultimately get? I ultimately got the word vectors for every word. I got these are the embeddings, right? Are you people with me? Did you follow?
Yes, sir.
So these are the final embeddings which I have got at the end of my training. And now what should I do? I should throw everything away and only keep this much, because this is what is my area of interest. Using this, I can make different kind of models. Like I told you, for example, the clinical test, or let's say I want to make a movie review application. I can use only these embeddings and I can make movie review applications. So this is what I was looking at. Now just for checking whether the embeddings are correct or not, let us have a test. So you see that my target word is juice. The actual context words are like, orange, and eat. And what is the predictions? The predictions are eat, orange, and like. It has predicted the words correctly, but it has lost what is the order. It doesn't care what is the order, because it has taken out the probabilities. According to the probabilities, eat has the highest probability, orange has the second highest probability, and so and so. So the first 4 words, it says you wanted a window of 2. So I have found a window of 2 in which these 4 words are the closest neighbors, and so they operate in this particular in this particular context. Is the machine working properly? Is my model working properly? Yes or no? Why are you all so silent?
Yeah. Yes, Pastor. Yeah.
Okay. Now I instead of just one, I will show you all the words. So you see that I have taken each word and I have taken the context and check whether the predictions are correct or not. Just have a check. Do you notice anything significant? Anyone?
The orders are reversed.
Not reversed. They are not in order. It is reversed. Maybe it is because the corpus is very small. It may seem like that, but
yes. For 1 and 2 instance, even it is not reversed. Yes.
But notice one thing. Look at the sum context probability sum. Look at these numbers. What do these numbers suggest to you? What do these numbers suggest to you? Anything it suggests? In what order are these numbers? 96%, 97%. What does it say?
And the highest confidence that we can have.
It has got a very high confidence in what it is doing, in what it has learned. Okay. It may still seem it may still so let us just check. Let us just compare what was the initial state and what is the final state. So initially you see it was predicting up to 50%. Now it is confident up to 96, 97% that it has learned the language. So this is the impact of training a machine using a particular model. Okay. Okay. Now let me take you to something more practical. Today I will try to show you not only English language, I will also show you Sanskrit language. So I want to impress upon you that this kind of learning, teaching what we are doing to the machine, it can span languages. It is not bound by a particular language. You see, without understanding a meaning of a single word, it can understand what words actually mean. Okay, now let us see a practical corpus. So I'm taking, let me just start this. What I'm going to do right now is that I'm going to take the complete works of Shakespeare and tell the machine, you learn the language from how Shakespeare is to write. Let me see whether the machine can learn or not. Oh, sorry. Okay. So we are teaching the machine Shakespearean language. Let us see whether he can understand or not. So okay. So I download the Shakespeare corpus. This is available in a database called Gutenberg. So Gutenberg has a lot of data. So if you want to experiment, you can do that. Okay, so you see that it has got 8 books of Shakespeare, and from these 8 books data, these are popular books. Okay, Hamlet, Julius Caesar, and all kind of stuff. So now what I do is that I do a tokenization. So I have found 28,700 tokens, and you see that these sentences like the tragedy of Anthony and Cleopatra and all things like that. Okay, now I train my skip-gram. So these are my training parameters. So this is a vocabulary of 3,000 words nearly, and I plot the most popular words. So you see these are the most popular words in Shakespeare. If you notice here, most of the words are very common words like U, I, D, and so I will get rid of these. That doesn't really show what Shakespeare is to write about. So what I do is these are called stop words basically. So if I get rid of the stop words and then I see the vocabulary, now it seems more like what Shakespeare is to write, like thou, thee, and word, well, man, and things like that. Okay, now I've taken this most common words of Shakespeare and I create my what happened? Eligible words is not defined. Pro words. What did I miss? Did I miss something? I must have messed up something. Yeah, I will fix it. Don't worry. Number of neighbors. Okay, let me ask ChatGPT for this.
Yeah, Partha, we have given this length of eligible words now. I think it is saying eligible words itself is not
No,
defined.
eligible words has to be a variable, which I have somehow deleted by mistake, most probably. So let me just ask ChatGPT where that can come from. So just 1 minute, we will fix this. I'm sorry for this. I was so tired after today's class that I didn't get a chance to recheck this. But I have all the data. I have it. Newsletter. Verify word embedding. Skip-Gram notebook. NN, Skip-Gram 2. Okay. Just 1 minute. Sorry for this interruption. I can replace it with a number. That is not a problem. I can replace it with 4 or 5, something like that. But eligible words must be a list of words. Eligible words. Let me try this. Do I have the model already? Let me just check that. Do I have the model? Yes, I have the model. Okay. Okay, we recovered. So I can get rid of this. So you see that for every word, I have found out the eligible words. Right? What are the eligible words? These are the neighboring words for each word. So is it able to do that? What do you guys think?
Yes.
Yes.
Okay, and it is very highly confident in what it is doing, right? Okay, now let us put it to a test. Let us put it to a test. Come on, I have messed up with this vocab words. It's not defined. This is also coming from the model. Okay. It's coming from the model. That's why it is. I did something which has messed it up.
Partha, just curious, these 3 dashes that you're using, this is like section break for ChatGPT, is it?
Yes, yes.
Or is this like very specific how ChatGPT understands, or it is just that you use yourself?
No. See, I am using a copy of ChatGPT which I am licensed to. Okay, and I have taken a very long period of time to make ChatGPT understand the way I communicate with him.
Okay.
Okay, so this is the training which I have given to ChatGPT.
Okay. So this is your like Partha specific section break.
This is my specific ChatGPT.
Okay.
Okay, that is why he understands when I use this. Like if I tell ChatGPT to write some prose, he knows that I don't like too many bullets and things like that. So these are all the specific training which I have done to ChatGPT.
Okay, interesting. Thanks.
But then it also bounds you to the ChatGPT, right? Not if you have to do Claude.
I use ChatGPT, I use Gemini, I use Perplexity, and I use them heavily, but I am not bound by any of them. But
Okay.
I bounce my ideas, I get good ideas from them, and then I am able to build on my own.
No, what I said was because you have trained this spaces 3 dots for ChatGPT. Do you do the same with Gemini and Perplexity as well?
Gemini is little difficult, and perplexity is not possible.
Okay.
So these are some nuances you must know about the different tools before selecting which one you will pay for.
And what about this Claude?
I have never used Claude.
Okay.
I do not use any software for which I do not pay. So now I already am paying. I got Perplexity for free from my Airtel subscription.
Airtel, yes.
Right, and
But
Gemini and
Claude is also good, sir.
I will
think
try.
Claude,
Yeah, I already spend a lot of money on this software, but I will check it out. It is becoming very popular. Yes.
yes. If you are, I mean, it gives very nice answer to the technical questions.
Yeah. Correct. Now look at this. It learned Shakespeare's language, and now check this. Do you think it has learnt it effectively? Just have a check. The words which are closer to each other, they have a similar meaning. Right? So do you think it has been able to group the words effectively?
Yes, Partha, it looks so.
Yes.
Fair, good, gentle, all these are grouped together.
Now, did you get the point that he does not understand the meaning of any of the words which is planted here, but he knows these are similar in meaning? Did you get that point very clearly? Yes or no?
Yes.
Okay. Okay. So now if I see the similarity of the words, I have something I have done. This model variables is somehow I've lost them.
Looks like there was a specific section of the code you have deleted it, so which would have already
One
pre-populated.
section I have deleted.
Yeah.
One section I have deleted. Okay, let me recover this also. Aditi, yes, your question, please.
Partha, it might sound stupid, but my question is that we are teaching the context based on the neighboring words of certain words, right? How it is able to make an understanding of similar words, like kind of synonyms, by associating itself with the context words.
See, the context words are what? Context words are words which go together, right?
Mm-hmm.
That is what is context words.
Correct.
Context words are words which go together, and by understanding which words go together, it is able to make out that these are synonyms, these are antonyms, and so on. Now this is messed up. Don't consider this chart. There's something wrong which has happened. I will try to recover this fully, and I will share with you. So anyway, I have recovered everything, but the last step is not recovered. Okay. Anyway, to answer Aditya's question, see, he does not understand the meanings. It is nowhere he's saying this is synonym, antonym, nothing. All he understands is that in this particular corpus, these words go together. So if they go together, they must be having a similar kind of a meaning.
Actually, I am having confusion with with what we are saying as go together, because generally I would not use good and fair in a same sentence, right? So they will not be generally they will not be neighboring words, is what I'm saying.
No. Good and fair need not be neighboring words, but there are words which is there in the corpus where in between which I may have utilized good sometimes I may have utilized fair sometimes.
And that connection also it is able to make. Okay.
Right. You see here, you see the words like this: Brutus, King, Queen, Hamlet,
Mm-hmm.
Caesar, Antony. I would have never used a word like Caesar, Antony.
Correct.
But it understands the
Yeah.
words which are surrounding it are similar. That is why these must be similar words.
Right.
Cassius, Mark, all are some royalty, right?
Yes, Partha, makes sense. Thanks.
Yes, Eknath.
So just thinking slightly on that, like, okay, I had been using Grammarly also. So Grammarly is nicely, like, okay, helping me in terms of paraphrasing the words or correcting my sentences and making more appropriate. So probably, like, okay, Skip-Gram might be heavily used. That's what I could sense or correlate. Not sure, like, okay, I'm right or wrong.
Eknath, I'm sorry to add to your question. It might also be trained on thesauruses and dictionaries, right?
Yeah, of course. It is basically like, okay, trained on thesaurus and dictionary, but the way, like, okay, it arranges the words, like, okay, it is reading my word and then recommending or suggesting another word,
True. Yeah.
and that recommendation potentially is like example, like, okay, in my line of one line has some context, and taking that context, it is in order to paraphrase and make new predicted word more appropriate, meaningful, or more refined, whatever is that. So probably, like, okay, Skip-Gram might be used, I'm not sure, but just thinking on those lines, if I know.
Eknath, the thing is that I have just started discussion regarding how I'm teaching the machine to understand a language, right? We are in the beginning stages. As we progress in the
Okay.
discussion, you'll see that there are much more sophisticated mechanisms which we will develop to make the machine understand our language, right?
Sure, sir. I understood. So I'll hold my thought.
Just hold your thought. You will get your answer. Don't
Sure.
worry.
Thank you.
Yeah. But this is something which is very, very powerful. Now let me show you another application. Now what I've done so far is only discussed with you English language. Now I'm going to discuss with you Sanskrit, right? So if I can do it in Sanskrit, you should be convinced that I can do it in any other language. Do you think I can espouse that kind of a confidence in you guys? Sanskrit is a very difficult language, mind you.
So the understanding is part of that. Since it's all mathematical operations, so it is not creating exactly the meaning of the word, but it is just for him. It's just the numbers. So that means this same logic can be applied on any kind of text or languages around the world, right? So
yes, that is the whole purpose. That is the whole purpose of this final presentation today, to tell you that using the same mathematics, I can teach him any language.
But keeping in mind that Skip-Gram is still not taking into consideration the order of the words.
Yes, we have still got problems,
yeah,
which even next class also we will not be able to solve.
Yeah.
One of the major problems which you have is that you notice here, for him right now, every individual word is a token, right? So you will come across, this question must come to your mind, like the things like, supposing I have the word run and running. I have some problem. Let me see if I can overcome this. Okay, if I have the word run and running, right now, for me, what is the language? Run is one word, running is one word. Maybe they are similar words, but they are two different words. But in my language understanding, I know that run and running is basically the same word. It is only the different form of a single word. So I have to now improve my mechanism by which I can make him understand that run and running are basically the same word. So we'll do that in the class after next.
Yeah, I think if we are following your classes, Partha, we can get that blueprint. We come with one problem, try to give a solution, but that solution is also not the final solution. It has its own problem. The next class will have the solution for that.
Yeah.
So if you keep attending, I think if we attend the entire classes, probably at the end we'll have some kind of a solutions that we can think, okay, yeah, this is what finally we should be able to apply on our LLM.
See, my goal in this particular program is that at the end of the show, you should be able to create your own LLM, and if it is possible for you, you should set up your company and give a competition to Claude and Gemini and ChatGPT. I will give you the complete technical and financial blueprint for doing that. Right. Okay, let's see.
We have a lot of confidence in us, probably, Partha, that we don't.
No, it's not difficult. Okay, let's start. So let's do the Sanskrit part of it now. So I go through the initial steps, download the libraries. Okay, we're done. So now this is Bhagavad Puran. Okay, I actually have downloaded the complete Purans because I'm researching on the Purans for my PhD in Indian knowledge system. So this is only one of the 18 Mahapuranas. So this is Bhagavad Puran. So I do some cleaning. This requires a lot of pre-processing. So I've done the cleaning and I have total of some 1.3 million characters, 1.4 million characters, and then I do some sentenceization. So you see that I'm getting the Sanskrit sentences. This, by the way, is a language called IAST. If you guys know a little bit about Indian knowledge system, IAST is basically internationally acknowledged Sanskrit transliteration. Transliteration, that is very important. It is not translation, transliteration. Now, what has been done is that when we discovered our old Sanskrit texts like the Vedas, Puranas, and all the kind of stuff, the Western people, they couldn't read it because they didn't have a very good knowledge of the Devanagari script. But some of them mastered it, and then what they did was that they made an English form of Sanskrit, in which you could read Sanskrit using English in these Roman alphabets, but without losing the meaning of Sanskrit. Right. So that language which they created was called IAST. It is called internationally accepted Sanskrit transliteration. It transliterates. It doesn't translate. So this is IAST. What you're seeing here, this is IAST. Okay. So now I have purposefully not taken Devanagari. I could have done that, but it would have taken a little bit more time to set up the experiment. So now I am doing my skip-gram here. So you notice that it is basically word-to-vec family, and in word-to-vec I'm using skip-gram. I can either use CBOW or skip-gram. I cannot use both of them simultaneously. Okay. So now I have got this, and I have got a vocabulary of now about 44,000 words, and now I display the words. Yes, Aditi.
Partha, how did you identify the stop words in Sanskrit?
Which are by frequency.
Only by frequency. Acha,
Only by frequency.
Yeah. Okay.
Okay. So you see, these are the words which are appearing in Bhagavad Puran, the maximum. I have removed the stop words like iti, tvam, etc. These are all stop words in Sanskrit. I have removed all of that. So these are the top words in this thing. Now I find the nearest neighbors. Okay. So you see that these are the nearest neighbors. Now this should not be difficult for you. Now look at this word asur, very convenient word because we all understand what asur is. Now look at the corresponding words. Nira Vidayata, Dushyaraj, Dusriyaj, Tut, Dampat, etc. These are, I'm telling you from my confidence that these are actually very similar context to Asur. So you can look at that, it has identified them quite nicely. Okay. Yes, Eknath.
So how do you deal with Sandhi?
That is a whole topic. So that is part of the reason I have broken that already.
Okay.
So
Okay.
I have solution for that. That is one of the steps which I've completed in my PhD. Okay. Maybe
Okay.
some other context I will take you a session on that.
Sure. Thank you, sir.
Okay, now let me plot the TSNE. So for the guys who have joined new, look at this. I am having these vectors which are of dimension 100. Now, 1 minute, let me just show you that. Yeah, look at this. These vectors are of size 100. Can I visualize vectors of size 100 on a two-dimensional graph?
No.
You cannot, right? So what I'm doing dimensionality reduction. I'm reducing 100 dimensions to 2 dimensions. That is why, without losing any meaning of the context, I'm able to show you the entire thing in 2 dimensions. This is dimensionality reduction. Right, now look at this. Do you think you can make out that the machine has learned the language effectively? Just try and make sense out of it.
Yes, it has put Dharma, Guru, Swayam in the same quadrant.
Yeah. Good.
Also Antapura, Jana.
So have you been able to teach the machine Sanskrit by this technique? Yes or no?
Looks like, yes.
Okay. Now let me show you some popular words. Let me see whether the contexts are captured correctly or not. Now look at this. So let's say a strong association. So this is 0.7. 0.7 is Bhagav, and here I have, no, this is not correct. Let me take a strong association. Ratha and Taman. Okay, I quite don't understand the meaning there. Let me karma. Karma, let me see what is associated strongly with. Karma with yate.
It also has a strong association with Deva, the same word.
Yeah. So see, it is the inner action of discipline. So it must be karma, right? Let me be more specific in my question. How does it relate to karma?
No, sorry, I was wrong. I read the wrong thing regarding Deva. Please discard.
The relationship between yate and karma is subtle but profound. It connects inner efforts and with outer actions. So they are related, right? You get it? Is it understood, the language? Now do you feel convinced? Okay, guys, that is all I have for today's session. I will do the sharing part now. And next class, I think will be interesting for you guys, because next class, what we will do is that we will understand another algorithm called glove. Now, so far, we've been dealing with local contexts, right? Next words, context, words around each other and things like that. In the next session, what we will do is that we will take global context. We will not restrict ourselves to local context. We will take ourselves to the global context. And in the global context, after we have established our what do you call word embeddings, we will create a system by which the machine will generate text for us, just like ChatGPT does for you. It generates text based on your answers. So we will also create a system by which we will generate text, right? We will give it a input, and we will say that please complete my sentence. Do you think that will be an interesting application?
Yes, live in action.
Yep.
So we'll do that in the next class. So, okay, I round off. I repeat my appeal. Please put some money into my account, because it takes lots of money to do research, and I'll be grateful to you. It's not mandatory, but if it is possible for you, please do that. For Indians, you can transfer to my UPI account. I'm becoming a little shameless right now regarding this, okay? Guys, I was very shy initially, but now I say this so confidently. Anyway, some change in me. So if it is possible for you, please transfer some money. It will help me do my research. So guys, thank you very much for joining. I hope you found it useful, and I hope to see you in the next class, right?
Yeah, sure.